Welcome student to the series of lecture on the large language model and the series of the lecture of large language model. Today we'll discuss and start the discussions of or the series of lectures within the LLM from scratch series on self-attention mechanism. Why? Why we are dedicating a series of lecture on self-attention mechanism? Because this self-attention mechanism is the engine of the large language model, the new age large language model. This is the reason, the self attention mechanism is the reason why you have seen exponential growth in the capabilities of large language model. Since 2014, when Badha Now paper came, since then, world got aware of attention. But in 2017, we got to know self attention mechanism in transformer, and that was game changer. And therefore, it is necessary that we dedicate a series of videos on self attention mechanism because, first of all, this is the core, this is the pillar, this is the meat of the discussion self attention mechanism. I'm not saying tokenization, vector embedding, positional embedding was not important. It was important. But if you really want to optimize your engine, optimize your LLM model, then you should dedicate a lot of time on self attention mechanism. And what I'm trying to do in this session, in the series of lecture on self attention mechanism, I'll try to discuss why, not just how. Why, the rationale behind the maths, the algorithm of self attention mechanism. And today, we'll start with that intuition, and that's why you see simplified self attention mechanism. And you won't find any single lecture on YouTube which is talking about the why behind self attention mechanism. Okay, so be prepared to build your intuition, which will help you to optimize your own LLM model. Okay, so till now we have discussed tokenization, vector embedding, positional embedding. Okay, so first we convert word into tokens, then vector embedding was, we can simply write it as semantic embedding of a token. And then we talked about positional embedding. And this is important for today's lecture because today we'll discuss those sinusoidal function, the sine theta, the cos theta that we discussed in the last session. It is important because we'll rediscuss in the self-attention mechanism today. Please visit that lecture, revise that lecture, and come back. Okay, now assume the word is I am a student of CS. Then what we know till now, we have the vector embedding of each token or each word. These are those vector embedding. Perfect. What information each vector has? First of all, it has the information of four characteristics, right? Each vector, each vector for each token has the information of the semantic, the characteristics, right? Because it is vector embedding. We discussed that in vector embedding, and it has the information of position. Because if you remember, we added what? Sine theta and cos theta in each vector in the positional embedding. So it has information of characteristics, it has important information of position. Perfect. But it doesn't have the information, this particular vector, which is the vector embedding for I, this doesn't have the information of where to focus the most. So, what is self attention? Self attention is that you have to focus on the same sequence. The token has to focus on the same sequence. The word has to focus on the same sequence. So, this is a sequence. This is the sequence of the token. And I has to focus on I am a student of CS. But where to focus more? Should I focus more on I, say 80%? Then I should focus more on CS, say 5%. Then I should focus on students, say 5% or 4%, and rest like 0.05%, 0.05%, or 0.005%, whatever. This vector, yes, it has the information of semantic, the meaning of I in the vector space. Position, yes, but it doesn't have the information where to focus because I never embedded that information in this vector. Yes, it is a vector, but this is not a context vector. What? It doesn't have the context. Why it doesn't have the context? Because it doesn't know where to focus. So I have to convert this vector embedding into context vector. A context vector is a vector which has the information not only of semantic, not only of position, but where to focus more to get the context of the sentence. So every vector that you see here, I need to convert it into from the simple vector to a context vector. And the context vector simply means that every vector embed the information where I needed to focus the most. Okay, perfect. Which simply means that I need to find out the attention weight or the attention score. What should be the weight given to I? What should be the weight given to am? What should be the weight given to A? What should be the weight given to student? What should be the weight given to off? What should be the weight given to CS? If I is my query, I'm talking about this vector. So this vector is my focus right now. So I will call it as query going forward. Because this query need to embed all the information about the context. So this query need to be converted into context vector, right? This query need to be converted into context vector. And the context vector need what? The weight given to each token, other token in the same sequence. And that is called as attention score or attention weight. And we have to find it. How to find it? How to find it? How to find these weights? So to find these weights, please understand this weight should have three information. Should have three information. It should have definitely the semantic importance between the two words or semantic weight. For example, if the sentence is I am a student of CS and AI or LLM, then I know CS and AI has semantic relationship. They are near to each other in the vector space. So the weight that I'm trying to find out should have that information. Number one, it should have positional importance or positional information. So I is very near to am. This information should be embedded into this attention score. This attention score should have two information. The first information is about semantic importance or characteristics importance, which simply means that how near two word is in the terms of meaning, in the terms of characteristics. So for example, if I try to plot all the words in the vector space, we know that CS and AI would very near to each other because they have a lot of semantic nearness or semantic similarity. I is near to am but farther from student. That is positional importance or positional information. The third information which is needed is context importance. Context is that if you talk about I, then it should understand that what is the importance of student in this whole context relative to I? What is this importance of am with I in the context of the whole sentence? So this weight should have three information: positional importance or positional information, characteristics importance, context importance. When I say importance, I want to highlight for the query vector, what is important? What is important should be captured in this weight. So your attention score should have these three information. Because today's session is a simplified version of attention mechanism, I will not talk about this, but I will try to highlight that how your attention score capture the positional importance or positional information or characteristics importance relative to each token. And the answer to that question is simply the dot product. If you do dot product between two vector, what I'm trying to say, I is my query vector, right? This is my query vector, QV, query vector. And I have to find out the attention score between I, then am, then A, student, so and so forth. Each one of the token has their own vector. If I simply do a dot product between I and I, I'll get a number. That number would be a single number, say 0.70. That is a weight. Then I'll do a dot product between I and M. That is going to be a weight. Between I and A, that is going to be a weight. Then I and student, that is going to be the weight. And that weight carry the information, the positional nearness and also characteristics nearness between two tokens. How come? Do you remember when we did positional embedding, we added sine 1 and cos 1 in the vector of I? For each vector, I added sine 1, cos 1, right? So if this is the vector for I added sine 1, cos 1, sine 1 upon 10, cos 1 upon 10. And for am, I added sine 2, cos 2, sine 2 upon 10, cos 2 upon 10. You remember that? I just added that information. But if today I'm doing a dot product, if I'm doing a dot product, at the end, what will happen? Sine 1 will get multiplied with cos 2, and cos 1 will get multiplied with sine 2. And when you do this dot product, what will happen? It would tell you that 1 minus 2 is minus 1. It tells you that I is just one position before am, and am is just one position after I. Because of this dot product, because dot product carry that information. So it's not that when you added sine 1 and cos 1, sine 2 and cos 2, then and there it captured the positional information. No, the real positional information, the relative information between two tokens get captured when you do the dot product. So this is number one. Number two, what about characteristics importance? When you do dot product between two vector, so assume these are two vector, v1 and v2. When you do dot product between two vector, you write modulus of v1 as in the magnitude of v1, magnitude of v2, and cos theta. If these vector are very near, which means that they have semantic similarity, they have characteristic similarity, CS and LLM, right? CS and LLM, they have semantic similarity. It means that cos theta, in this cos theta, the theta is very near to what? 0. They are very near to each other. So cos 0 will become 1. However, they are not related to each other. They're far apart. They're orthogonal to each other, as in they are in two different vector spaces. Or you can simply say that it has 90 degree between them, orthogonal to each other. If you do cos 90, then it will become what? 0, which is telling you that they are orthogonal to each other. There is no relationship between vector 1 and vector 2. There is no semantic relationship or nearness between vector 1 and vector 2. So both the information, the positional importance between I and am get captured, and the semantic importance between two token gets captured with the help of this dot product. But yes, it doesn't capture the context importance. How am is important in this whole context relative to I. This is not getting captured. I agree. But this is the simplified version of attention mechanism. We'll discuss that in the next session. Now, when you do this dot product, what you will get? You will get the weights. You will get the weights, right? So when you do the dot product between the query and the vector, you will get one single weight. Weight 1, weight 2, weight 3, weight 4, weight 5, weight 6, weight 7. But still you got what? Weight, not the context vector. How will you get the context vector? The simple answer to this question is you will multiply this weight not to the query vector, but to individual vectors. The attention score of I will get multiplied to the vector embedding of I. The attention weight or attention score of am will get multiplied with the vector embedding of am. The attention score of A will get multiplied with the vector embedding of A, and the attention score of CS will get multiplied to the vector embedding of CS. And then you will add each one of them. And that will give you a final vector for this query vector, that is 0.60, say 0.70, 0.83, 0.53. This is your context vector only for I. You have to repeat this exercise for am, a, student, of, and cs. So in the next iteration, am will become the query vector. Then you will try to find out the attention weight for each token for am. Then you will multiply the attention weight that you find with the dot product to the vectors. Then you sum it up and you will find the context vector for am. So the final step is what? Weighted average. Weighted average of all the vector embedding. So at the end, it is the weighted average of all the vectors. That will give you the final context vector for your query vector. And you have to repeat this exercise for all the query vector or all the tokens. What is actually happening? If you try to see it on a vector space or a two-dimensional space, then what is happening? This was your query vector. This was your query vector, right? Now these were your other vectors. Am, say, student, of, cs, right? This was not a vector. Now what you're doing? When you're multiplying I with I, it is giving you a weight. Say that weight is 0.60. If you multiply 0.60 with I vector, then this length of this vector gets shortened by that weight. Okay, so you are assigning a weight of 20%. Here you are assigning a weight of say 10%. Here you are assigning a weight of 5%. Here you are assigning a weight of 5%. Here you are assigning a weight of 30%. Here you are assigning a weight of 40%, say. Now this am will get reduced by the weight of 40. Then CS will get reduced by the weight of 30. Then A will get reduced by the weight of 0.05. Off will get reduced by the weight of 0.05 as in the magnitude. And student will get reduced by the magnitude of 10, 0.10. And then you add each one of them. You add each one of them. You add each vector. That is weighted average. And finally, you got a new context vector. A new context vector. This context vector is the context vector for I. And you have to repeat this exercise for am, a, student, of, and cs. Okay. And this is the complete story. But you need to normalize these weights. Why you need to normalize these weights? Because it will not sum to 1. So you need to normalize. So there are two methods to normalize. One is you do what? Weight 1 upon summation of all the weights. You can normalize in this way. And the other approach is softmax. In softmax, what you do? You do e to the power weight 1 divided by summation of e to the power weight I, where I varies from 1 to 6 because there are 6 different vectors. Okay. Even the actual softmax is, you can also do e to the power weight of I minus max of all the weights I divided by summation of e to the power wi minus max of wi. So these are the different methods to normalize the weight. The sum of all the weights should be equal to 1. And the second is it reduces the problem of outliers. Okay. The story is very simple, which can be explained in one line. That dot product between two vectors will give you a weight. And that weight is your attention score. That's it. If you multiply that weight to individual vectors in a sentence and you sum it up, you will get context vector for your query vector. Currently, our query vector was I. Our query vector was I. You have to repeat this exercise for all the vectors, all the tokens vectors to find out the context vector for each token. You do it for I, you do it for AM, you do it for A, you do it for student, you do it for off, and you do it for CS. So that was our very simplified discussion on self-attention mechanism. Thank you. Have a nice day.